Okay. I've got the exams graded. Some of you definitely need to work on your stapling skills. When you're putting the staple like 3 inches from the corner. No, no, okay, just no. We'll get them back at the end of class. Be like the last 15 minutes we do in class today. We are still talking about ANOVA. And we can use ANOVA the same way we can use a two-sample t-test, but we can also make it three-sample or three-sample or more if we want to. We'll actually take a look at that. When you look at ANOVA, when it comes time to actually answer some of these questions on an exam, one of the things that's going to happen is we're going to have an ANOVA table. So basically, we're going to have a row for what we're going to call a model, a row for what we're going to call an error, and then there will be a total. We'll be looking at degrees of freedom, what's called sum of squares, what's called mean sum of squares, which is this MS, and then we're also going to be looking at an F value. The total degrees of freedom down here is just going to be capital N minus 1. And if you remember from before, I said like N equals the number of samples in group A plus the number of samples in group B. Well, we continue on with this. So number of samples in group C, number of samples in group D, and so on. So if I have 5 groups with 12 subjects in each one, 5 times 12 is 60. What we put in there, 60 minus 1, so 59. Up here, uh, number of terms or groups that we have, again, minus 1. So again, if we have 5 groups with 12 subjects in each one, down here, this is going to be 59. Up here, it's going to be 5 minus 1, so that's going to be 4. And then error here is just going to be the difference. So degrees of freedom from the model plus degrees of freedom from the error are going to be degrees of freedom total. So if I have 59 here, I have 4 here. 59 minus 4, 55. Not too hard a math yet, right? And we'll actually work on these. And I will say, when you work on the problem, it's going to be on you to figure out the values to put in all 3 of these cells. With sum of squares, we again have sum of squares model plus sum of squares error equals sum of squares total. For this one, I have to give you 2 of these, you figure out the third one. So if I say sum of squares model is 100, sum of squares error is 300, what's sum of squares total going to be? 400. This MS stuff over here, we don't need to worry about that at all. We don't need to worry about that at all. But this is just whatever the sum of squares is divided by degrees of freedom. So in this case, sum of squares model divided by degrees of freedom for the model. Here it's going to be sum of squares error divided by uh, degrees of freedom error. And then out in here, mean sum of squares for the model divided by mean sum of squares for the error. You then get that as your uh, or your calculated number. You compare it against critical values on a table somewhere, and you determine whether or not the model that you have is trying to suggest there happens to be a significant difference between one or more of the groups. With these ANOVA, we are again doing hypotheses tests. We are assuming the average for group A equals the average for group B equals the average for group C, and so on. The alternative hypothesis, one group or more is different from the other groups. So to give us an idea about what this looks like, I'm going to scoot this off to the side and then try to zoom in a little bit. Oh. So thought I had the information up here, apparently not. So we'll do it this way. And I'm using Excel with this just so that I can actually zoom in and we can see what's going on here. I said previously that with Excel, uh, it does ANOVA, but it kind of skips some of the stuff we talked about last time. We'll go over that again this time, so don't worry about it too much. But I can come on here, I can go to data analysis, and I'm going to do a two sample t-test assuming equal variance. ANOVA, again, we have to assume there's equal variance here. So I can click on OK. And I'm just going to say medication A versus, let's see, I think it's, no, medication F here. I have labels, blah, blah, blah. So look at that. And this is the outcome that I get from looking at two sample t-test, again, assuming equal variances. I can do the same thing with ANOVA. With ANOVA on here, though, it is a little bit pickier. Not yet. I'm just using it as a demonstration. And we're going to work with Minitab next time, so you will have some data like this to work with, so we can actually go through it and make sure you know how to analyze the data and everything. Now, if I go back here, I can go back to ANOVA single factor. My input range is just going to be these two things. Labels in the first row, going to click on OK. And we get essentially the same thing. So when you look at the information that we have here, though, they're calling it uh, between groups and within groups. When we look at ANOVA tables for regression models, it's model versus error. So we can think of that top part as the model. This bottom thing here as the error. And when you look up here, again, two groups with 10 samples each, 10 plus 10 is 20. Degrees of freedom total is 19 because 20 minus 1. We've got two groups, so 2 minus 1 is 1. Down here, we've got the difference between those two. And for whatever reason, when you do ANOVA with Excel, you get the table that looks like this when you get, or when we do the same thing with regression models. Again, we're going to get another ANOVA table, and degrees of freedom and sum of squares are going to be basically flipped over. So looking at the value here, what's this number divided by 1 going to be? Whatever that number is. This number here divided by that number, about 270. If we want to check it, it's a sum of squares divided by degrees of freedom. There we go. And then the F-test here, again, it's the value on top divided by the value on the bottom. And this is telling me that the F value is really, really small. So the p-value for this test is 0.994. So that's basically telling me there is no significant difference between these groups. And with Excel, it actually gives you the F critical value that you can compare it to. So when you look at everything here, my expectation for all of you, and we're going to do some examples of these, is that you can calculate these three things. You can calculate, say, one of these things in here. These things, and then that thing. So on a problem like this, it's 2, 4, 6, 8, 10, 12, 14 points just getting this one table done. Now, when we're looking at this data as well, this 269.64, if we compare that to the pooled variance for the two sample t-test, it's the exact same value, which means these two things tell you the exact same thing. And one of the things that you have to do with this after you've done all of, or taken care of all of this, we have to go back and we have to make comparisons, or we can make comparisons. This is telling us straight up there's nothing different, so don't even bother with it. That may or may not be a trick question on an exam. If we see that the p-value is below, say, 0.05, 0.01, whatever value we choose, then you start going in, then you start doing the multiple comparison tests that we were talking about last time. Another one of the big mistakes I see a lot of people do with ANOVA is they will start running multiple comparisons, even though ANOVA says there is no difference. But they will do anything they can to try to find a difference, because once you find a difference between some of these groups, you have an opportunity to write a journal article about it and get it published. Your article will be complete garbage, but that doesn't matter because you got a publication. So you have to watch out for that. With the mean sum of squares here, with the pooled variance that's here, You can take the square root of that, get the standard deviation and everything else. But if, let's say we're looking at the data here and we did find that there was a statistically significant difference here, one of the things we would have to do is we've got the averages, we've got n, we've got variance, and you can see here that the variance between these two is very, very different, meaning ANOVA is not a good choice for this particular type of a test. Minitab should have some options on there to make this a lot easier for us to tell if ANOVA was done properly or not. Some of the stuff I teach my other students, it the software actually comes up and says, you do not have homogeneous variance. Just to let you know, don't trust the results that you just got here, okay? But if we're going to do, essentially, when we do those multiple comparisons, what we're doing is what? We're trying to come up with two sample t-tests. What all do you need with a two sample t-test? You need two averages, you need two n's, and you need two standard deviations. Does anyone remember how to go from variance to standard deviation? Just take a square root. So I will say right now the ANOVA problem that's going to be on the next exam and the ANOVA problem that's going to be on the final, probably about 60 or 70 points each. So I'll make sure that we go through how to do these a couple different times. And if we're just trying to do a simple two sample t-test with the information here, what do you think the biggest mistake previous students have made with this? They'll end up using the variance values instead of taking the square root. How do you take the square, if we're doing this in Excel, how do you take the square root of these? You can actually say equal SQRT, open parentheses, click on whatever, close the parentheses, and that is the standard deviation right there. And that is the standard deviation right there. Now with the ANOVA, I'm going to go back and redo this again. So ANOVA single factor. Again, I'm doing it on Excel just so that I can actually zoom in and you can actually see everything that's in these tables. We're going to be doing it with Minitab just to do everything properly. So I'm going to click on OK. Now I have all of my information here. And again, we see here that the p-value is well above 0.05 or 0.01, whatever number we're actually looking at. So that's telling us that there doesn't seem to be a statistically significant difference between any of these groups. So if this pops up on one of the exams, did you find anything significant or any significant differences between the groups? The answer is just straight up no. For exercise purposes, can always ask you, despite whether or not you found something significant here, perform two sample t-tests with everything else. And instead of the issues that we're talking about last time, I'd only have you do like say A versus C and B versus E or something like that. So not looking to have you redo every single thing that's on here. But just as a for instance, group C has the largest value or the largest average. Group E has like the smallest average here. Again, if we're going to be doing this on a test, You need to figure out what goes in these degrees of freedom here. You need to figure out what goes in these sum of squares and what goes over here. You can see the F critical value off on the side. That's going to give you an indication about whether or not the value you just calculated for here is important or not. So we will look at that. But we've got our two groups here. Plug those values into your calculator, and you can go ahead and figure out what is the t value for that? Does there seem to be a significant difference between those two groups and that sort of thing? So getting back to something like this, just so we can have a little bit of practice with what you're going to be expected to do on an exam. So we have a row for the model, a row for the error, a row for the total, degrees of freedom, sum of squares, mean sum of squares, and then at the end here, an F test. So if I have, say, group A, B, C, and D, and the count for each of these is, say, 20. DF total is going to be 20 plus 20 plus 20 plus 20. So 80 minus 1. DF for the model, again, is going to be the number of groups. And then whatever we have here for the error is going to be the difference between these two. And like I said, when we're doing these, I have to give you, say, at least two of these. So let's say we have sum of squares total is 1,000. Sum of squares for the error is 800. Now I'll underline these so that we know which values you are actually expected to calculate here. So what's my sum of squares model? So 1,000 minus 800. It's going to be 200. So mean sum of squares, the value here, is going to be sum of squares for the model divided by degrees of freedom for the model. Mean sum of squares error is going to be sum of squares error divided by degrees of freedom for the error. So it's 200 divided by 3 right offhand. Anyone know? Exactly. Probably should have thought these numbers through a little bit better. Well, whatever. It's called a calculator, right? And we all know how to use a calculator, I hope. So uh, we've got, move this off to the side a little bit more. So to do the mean sum of squares for the model, so 200 divided by degrees of freedom from the model, 3. So 66.67. Mean sum of squares for the error, 800 divided by 76. So this is going to give us 10.53. With mean sum of squares and the f-test, taking everything out to 2 or 3 decimals is going to be more than enough. And then the f value is going to be mean sum of squares from the model divided by mean sum of squares for the error. So in this case, 66.67 divided by 10.53. So that's going to give us the 6.33. Make that bigger so that everyone can kind of see where that's coming from. And like I said, on the exam, there's going to be 1, 2, 3. Something in here is going to be calculated by you. So that's going to be 4, 5, 6, 7 things. So that right there is 14 points on the next exam and 14 points on the final. So we'll have some more of these, okay? Does everyone have all of this copied down? Okay. So 6.33, we need to keep that number in mind for a moment. Unfortunately, for exam purposes with this type of a problem, you're not going to be given a p-value, but you're going to be expected to try and figure out, do we have a statistically significant difference here? With an f-test, it looks something like that. And at a certain point, we'll have something, I'll call it F critical. And I'm just making up a number here. Well, let's say that's 4.0. Now, with p-values, with everything that's done to figure out reject or fail to reject the null hypothesis, since this is an f-test, if you get 0 to 4 that you calculated, we can say we failed to reject H naught. We do not believe there's a difference between the groups we're looking at. If you want to sound like a statistician, if you want someone to actually understand what you're saying, they're all the same to me. Or they're not different enough, which means what? Well, maybe if we had more data, we might actually find that there is actually a difference between these groups. We have a value that's 4 and beyond. We reject H naught. We have enough information to show that there does, or there seems to be a difference between groups here. Okay. So what was the f-test value we had? So the f-test value we calculated from the ANOVA table was 6.33. Do we reject H naught and think there's a difference? Or do we say we failed to reject H naught There is no difference. Well, it's out in the rejection area, right? So if we have any value in this case from 4 to positive infinity, we reject H naught. Once we've gotten to the point where we can say we reject H naught, the next step is and software is going to take care of all this stuff for you. But for exam purposes, instead of having, say, a test or one example problem where you're doing a t-test, one example problem where you're doing ANOVA, you can actually combine all these things together into one. Is it annoying? Yes. But would you rather have 2 problems that are worth 40 points each or one problem that's worth 80? Does it really matter? So looking at what we have here, we know that uh, we're rejecting H naught. So now we go back to the table that we were looking at. So you'll be given a table that looks kind of like this. So let's say, for instance, I tell you to do a comparison versus group A and group C. You're going to have a count based on what I said previously. There are 20 samples in each one of these groups. Uh, let's say the average for A is 10, the average for C is 18. And let's say the variance for group A is, I don't know, say 36 and 49. Now we can do a t-test with this, but again, what is the thing that we have to do here? You have to turn the variances into standard deviations. So standard deviation 30, square root of 36, it's going to be 6. Square root of 49 is going to be 7. So when you look at 49 versus 36, it looks like there's a huge difference between those two things, right? But when we look at the standard deviations, is it that big of a difference? No. So it's one of the reasons why you're supposed to do the F-test or the 2 variance tests, or with ANOVA, you have to check the variance of everything to make sure that they are similar enough. Now we've got the information we need to put it into a t-test. You all did t-test on the last exam. I'm not going to bother with it here, except what's the one other thing that we have to really deal with here? From what I was saying last time, the probability that you get all your comparisons correct is essentially the probability that you get each pair of comparisons correct raised to the number of comparisons. So if I have A, B, C, and D, I'm going to have AB, AC, AD, BC, BD, and then CD. Since I've got D all up in all these other groups, I don't need to worry about it. But what do you notice about the pattern that's going on here when we're looking at the number of comparisons? For A, it's the number of groups minus 1. For B, it's going to be the number of groups minus 2. Number of groups minus 3. For the fourth one, number of groups minus 4. So if I give you 8 groups to compare, how many are you going to have when you compare group A to the other groups, how many comparisons are you going to have? 7. What about for B? 6. What about for C? 5, and so on. So go 1, 2, 3, 4, 5, 6. So number of comparisons in this case is going to be 6. And if I tell you I want this to be, say, 90%. So I want not at least 90% of my comparisons to be correct. So when I talk about them as being, say, statistically significant or not statistically significant, I'm okay with getting 90% correct. Now I need to come back and calculate the p-value with this pair. So I've got 0.90 equals x to the 6th power. So x is just going to be the 6th root of 0.9. If you know how to do that in a graphing calculator, feel free to do that. If you're trying to use, say, your cell phone calculator, you just raise it to the power of 1/6. So we go back to, did I already get rid of the calculator? Geez. So I can do 0.9 raised to the 1 divided by 6 power, hit enter. And I'll just call this 0.983. That is going to be the new significance level for all the pairs that I'm looking at. So even though I said I want to do this at the 90% confidence level for all the comparisons, when I start looking at every single pair that I've got here, I actually have to put into the calculator significance level. It's going to be 0.983, not 0.95, not 0.90 or whatever. It's whatever value we just got here. And 0.983 versus 982,593,1939. I'm fine with 3 decimals there. On the other hand, and this is something that has actually happened before, if you have 0.999999993, you better put in for your confidence level 0.9999993. Because if you round that up to 1, it's wrong. So again, when it comes to the number of digits that you need, 3 digits is going to be more than fine here. But if you get a whole bunch of 9s in a row, you better take it out till that last value is not a 9 and go from there. Okay. So now that I've got that information, you can do this with a Minitab. Again, when you do ANOVA tests in a Minitab, it's going to do all this stuff for you anyways. So I'm just doing this to show you as an example of what's actually going on here. So 2-sample t-test. My average for the first group was what? So my average for the first group is 10. Standard deviation for that is 6. The number of subjects there is 20. For the next group, it's 18. Standard deviation for that group is 7. Again, we're looking at 20. For this, because ANOVA assumes that you have equal variance, we can go ahead and use the pooled yes, or the equal variance assumption. So you might have to actually click that box in Minitab. Then I can click on calculate. And it's given me this t value. It's given me this p value here. I now have to compare this p value against the p value I would get from this thing. So I'm just going to write this down real quick. I know that you can't see it yet. I'll move my hand or move this out of the way in a moment. So my new significance level for this test is 0.983. The p-value that was calculated is 0.004. The p-value to beat is going to be 1 minus the 0.983. So basically what, 0.017 is the value that we just calculated smaller than the p-value that we have to beat here. Yeah. So that's telling us that there is a statistically significant difference between groups A and C based on the data that I gave you. If I want to do the confidence interval, go back to stat. Oops, gotta go to tests. Two sample t interval. All my information is going to stay the same except the new confidence level that I need here is going to be 0.983. And our confidence interval for this is -13 to say -3. So we expect there to be a difference between say 3 and 13 units between the two groups we were looking at. That's all we can really say there. Like I said, with Minitab, when you put this data in, it's all, or essentially it's all going to be done for you. There are actually a couple different ways that we can do these comparison tests as well. But the big thing here, again, for purposes of the exam, you need to calculate the new significance level and then compare the p-value of this two sample t-test versus the p-value that you just calculated. And that I will say too, when we look at something like that, and you come out and you find that there is a statistically significant difference between the groups that you're dealing with, ANOVA is just trying to tell you what it thinks is happening. Because of all these multiple comparison corrections we have to make, which is this whole thing here, there will be times when you go and you look at every single comparison that was just done by the software, and there will not be a single statistically significant difference between any of the groups. ANOVA says there should be, but you will not be able to find it. It is something that comes up. It is something that I've seen before. And when we're doing these corrections tests for multiple comparisons, it's the formulas that are used are similar to this. They're not exactly the same thing. But what ends up happening is you can do compare those four groups against the best. So there's only going to be 3 comparisons. You can compare everything against a control. And I will say, if you do the everything against the control, you might find that, say, group B is less than group A, and group C and D are both a little bit more than group A, but there's not a big difference between A and B, A and C, and A and D. So your analysis will show, even though ANOVA says there seems to be a statistically significant difference between groups, because you did everything against a control, it might not actually find anything. The comparison you might want to do, or the comparison that it found to be different, might be B versus D. But you're not comparing B versus D. You're comparing A versus B, A versus C, A versus D. So a lot of weird things can come up. Just gonna be honest, when I make all these data sets and give you everything to try to solve all this stuff, I just put numbers down. I don't actually like try to make it so that this happens or that happens. It's just whatever happens naturally is what happens. So I don't even know what the answer is to the problems I give you until I actually go in and solve it. Okay. So like on the exam, I don't know what the answers are until I went and did the exam uh, yesterday morning while I was watching another group of my students take their exam. So with there are all these situations that can come up with ANOVA. Can they be tricky? Can they be a bit difficult to understand and try to deal with? Yes. Like I said, we will look at all of that stuff with um, ANOVA next time. But I can flip that over. Since I've got your exams ready, and they are